And so last time I spent the whole time talking about just conceptually what it means when we're talking about the impacts of climate change on the economy and how we tend to measure that in monetary dollars and what that actually means in terms of like impacting society as a whole. But today I'm going to go into some of the details and some of the specifics of what individual sectors of the economy we think are most sensitive to climate change and how that tends to be modeled, how that tends to be estimated. And we'll see that it's pretty complicated and pretty uncertain. So on my topic diagram, moving on from our weather and climate extremes into our socioeconomic impacts side of things. And so this is really where, I talked a lot about last semester how this connection between, industrialization, the use of fossil fuels, the increase in greenhouse gas concentrations, the increase in temperature, these are, as close to scientific facts as you can get. They're just very straightforward scientifically, which is where that 98% consensus comes from, which I actually think kind of undersells it. Like it's not going to be overturned that CO2 causes the temperature to increase. I mean, it's just a fact. And then we talked about it gets more complicated when it comes to connecting global temperature to some of these extremes. Some are less complicated, like heat waves, and some are more complicated, like tropical cyclones. Tornadoes tend to be really complicated. But it gets even harder when you're then making the connection between weather and some of these socioeconomic impacts. And we'll see that today, that we're moving away from parts of the science that are like physical laws, right? That this is a physical law that CO2 interacts with radiation a certain way and causes the Earth to accumulate energy and for temperature to rise. Where these connections between weather and energy use by humans, for example, are not physical laws. They're you can observe different patterns of behavior and you can account for technologies and things like that, but it's not something that's just like definitive, write down and prove it, for all of time, like it is with physics. So going back to my main points and questions that I brought up last time, just to ground ourselves before we look at some of the specifics of the economic impacts of climate change, I was talking about how at first glance it appears that both the costs of climate change on the economy and the costs of climate change mitigation policy might seem like they're just transfers of money. They're transfers from some place to another place, from A to B, rather than having like a net effect on the economy as a whole or on society as a whole. So some examples of that would be, isn't the monetary cost of rebuilding a house just the monetary benefit to the construction company? Isn't the cost of taxes, to the public, the benefit of wherever those taxes are going, like to, for example, a wind turbine manufacturer, if the taxes are part of a climate policy that's going to promote wind energy? Isn't the cost of my energy bill increasing if it's getting hotter? Isn't that just to the benefit of the utility company? And the answer to this was, if you kind of zoom out and think about climate change from a 30,000 foot view, the answer is when you have to reorganize society and divert resources to solving a problem, there is an unseen opportunity cost to that. And so two phrases that get used are opportunity cost and foregone production. And they both basically mean the same thing, that like if you have to divert resources to something in society, they're going to be diverted away from something else. So you're losing production and value someplace else. And I was reading this paper yesterday, this report on the cost of wildfire in California, and I came across this paragraph that says the same thing. And so I thought I would just read that so you can hear it from someone else's words. They say, it is also important to keep in mind when discussing the economic impact of wildfires that repairing and rebuilding damaged assets may appear in data as an increase in economic activity. For example, rebuilding destroyed homes will boost economic activity in the construction sector in the short run. However, this increase in economic activity in certain sectors in the short run has an opportunity cost of foregone economic activity in other parts of the economy. A full economic welfare analysis of wildfires would ideally measure these opportunity costs when considering the broad economic losses associated with wildfires. So when economic models, mathematical models, try to incorporate the damages from climate change, they do the damage on GDP. And that's accounting for this. It's saying that the entire economy shrinks a little bit from climate change because you have to redirect resources to things that you wouldn't have to have otherwise. So I have some class learning outcomes today around that concept. So the first thing, the main thing that I'm going to be talking about is this introducing this terminology, the damage function. So I want you to be able to define what the damage function is. And then all this other stuff is related to the damage function. So there are different ways of trying to quantify this damage function. There's a bottom-up way and there's a top-down way. So I want you to know what the bottom-up, know what a bottom-up assessment of this damage function is, or climate damages is. Know some of the major sectors of the economy that are typically included in this type of an assessment. Know what some of the downfalls of doing this type of an assessment are. We'll talk along the way about some of the weather and climate extremes that cause the most damage in the United States. And then this other way, this top-down assessment of climate damages. Know what that is and know what some of the downfalls of that are. So first, what is this damage function? So this is actually in En-ROADS. So I'll just show you this in En-ROADS. If you remember in En-ROADS, we did look at GDP per capita using the Kaya identity. So that was one place we saw GDP per capita. But another place that we can see it is if we go into assumptions. You go into assumptions and you go to economic impact of climate change. We have some settings we can play with: reduction in GDP at 2 degrees Celsius from climate impacts, and then maximum reduction in GDP. And let's see, related graph. Let's look at, okay, reduction in GDP versus temperature. So this right here is the damage function. The damage function is relating global temperature change to the percent reduction in GDP. And they have 1, 2, 3, 4 lines on here. So they're showing 4 different estimates of what that damage function might be. And so you can see that the estimates vary extremely widely. So one estimate by Bill Nordhaus says that at 4 degrees Celsius warming, you get a 4% reduction in GDP. Nicholas Stern and Dietz say that at that same 4 degrees global temperature warming, you get a 53% reduction in GDP. So huge range here. We see like different shapes of these functions, where some start off growing really fast early, but then they kind of saturate and stay steady, or some only take off much later, but then there's kind of some saturation effects, and some seem exponential. So that's just representing a lot of uncertainty there. The different groups have come up with very different estimates. Something that's interesting is we can, let's see, so like if I were to say, let's say we are going to use this Burke estimate here, and so it's going to follow that actually does reduce temperature, right? So we're damaging our own economy and we're reducing temperature by shrinking the economy and having less emissions that way. So that's obviously not an ideal way of doing that. But you can simulate, what would it be like if you just had total societal collapse and you just said, okay, at 2 degrees Celsius, you have 100% reduction in GDP. And then you see what that does to emissions. And so you can meet Paris agreements by destroying the world also, but that's obviously not the way that we want to do that. But the main point here is that this is the damage function, and so it's very uncertain, and there's different groups come up with different answers, but it's just the relationship and the reduction in GDP. The relationship between that and temperature change, so global warming. And so these estimates can be kind of sophisticated, and then what you're seeing is a line that's like, when you add up a bunch of individual parts together, it comes up with this line. Or they can be very, very simple. And so this Nordhaus one is one that's actually super, super simple. And this is a figure from my paper that I brought up last time that shows the entire Bill Nordhaus model, which this model is actually what Bill Nordhaus won the 2018 Nobel Prize in Economics for. But it's a super simple model, even though it kind of looks complicated here. This is the whole world in just a handful of equations. So it's like basically as simple as you can possibly get. And he basically designed this framework in the 1970s. And it's kind of the framework that climate economics still uses today. And so he didn't win the Nobel Prize for like the damage function. So the damage function could be much larger in his model. And people do mess with that in his model. But I just wanted to show you that this is what that damage function is mathematically in his model. It's just one super simple equation. And all it says is that damages to the economy are related to temperature squared. So as temperature gets larger, you damage the economy more, and you have a nonlinear relationship, a power law relationship, so that like, moving from +1 degree to +2 degrees is a certain amount of damage, and then moving from 2 degrees to 3 degrees is much more damage because you're squaring that. So that's like the super, super simple way of representing that. And then they try to tune that to like match what other estimates are that are more sophisticated. But you can try to come up with estimates of this that are more sophisticated, that have more equations that are trying to model and represent more things. So take a second to think about that. Like, what if you were trying to mathematically come up with representation of damages to the economy from climate change? Like, what sectors or what parts of society do you think would be most impacted? But this type of list is what a bottom-up assessment of climate damages is that you are kind of thinking about the different sectors, and then you're like individually going to go in and look at what is climate change's impact on agriculture, what is it on energy, what is it on sanitation, and then I'm going to come up with an estimate of those three, and I'm going to add them together, and then that's going to be my damage function. So bottom up is going sector by sector, making the estimates and then adding them together to get a damage function. And so let's just look at some of these sectors from just a few papers. So here's something that's trying to be comprehensive. This is from a paper called Climate Damages and Adaptation Potential Across Diverse Sectors of the United States. And so they have this table with these different sectors and then different subsectors within them. So they do water resources, agriculture, ecosystems, health, infrastructure, and electricity. Those are their big sectors. And then they have subsectors within each one of these. So water resources, they talk about damages from flooding. They talk about effects on water quality, water supply at the city level, and for industries, winter recreation, so changes in snowpack. Agriculture, obviously kind of just the impact on yields. Ecosystems, they have broken into coral reefs, shellfish, freshwater fish, wildfire. Health, you can think of a bunch of different ways health might be affected. So air quality, things like ozone, for example, which are bad for respiratory systems, that's temperature dependent. So the hotter it is, a lot of times you'll have more air quality problems with ozone. Allergens, extreme temperature mortality, labor. This is an interesting one that we can measure that people are less productive, they get less done when it's super hot out, especially obviously if it's like outdoor activities, but even in non-air conditioned indoor activities like call centers and things, so you can measure that productivity goes down when it's like 90 degrees as opposed to 85 degrees or 80 degrees type of thing. So people are less productive when it's hot. And then you have things like vector-borne diseases, changing locations with climate change, infrastructure, roads. And then here's our electricity demand and supply. So a lot of the things you mentioned are on this list. Here's another way of breaking out the sectors. This is actually not a study on climate change impacts, it's more just on weather impacts on the US economy. And so they break it out like this: agriculture, communications, construction, finance, insurance, and real estate, manufacturing, mining, retail trade, services, transportation, utilities, wholesale trade. And just to tell you what these numbers are, they're looking at temperature effects from heating degree days and cooling degree days. So heating degree days are when it's colder than 65 degrees and you generally need to heat your house or your building. And cooling degree days are when it's hotter than 65 degrees and so you need to cool your building. So that's just what they end up using for their measure of weather variability. And then they use precipitation variability as well. And then they're just looking at, what do these sectors do in terms of their output? And this paper looks at gross state product instead of gross domestic product. So they look at the state level. And the way that this is expressed is the numbers reported show the percentage change in gross state product when the weather variable increases by 1%. And so this negative 0.19 here means that when cooling degree days, when it gets hotter, when cooling degree days increase by 1%, agriculture decreases by 0.19%. We see there, just from weather variability, that agricultural yields decrease, or its productivity decreases when it's hotter. So this is another way of breaking out different sectors. Here's another way of looking at different sectors. This is from a global climate economics model called FUND, which stands for Framework for Uncertainty, Negotiation, and Distribution. But it's one of these models that are called integrated assessment models. And so their sectors are these 12. They have agriculture, forestry, water resources, energy consumption, sea level rise, ecosystems, 3 dimensions of human health, which they break out into diarrhea, vector-borne diseases, cardiovascular and respiratory mortality. They have 2 dimensions of extreme weather, which they break out into tropical storms and extratropical storms, and then just general mortality and morbidity associated with temperature itself. So that's the way this model breaks it out. So one point I'm trying to make here, this is kind of going back to some of the downfalls of bottom-up assessments, is that there's no like consensus of like what sectors to look at and what sectors are the most important. And you'll see that there can be some double counting sometimes, or it's not clear like what, you see some impact, what sector that should go in, that type of thing. But let's just like go through this a little bit and think about these, because I think it helps us refine our thinking in terms of how climate change might impact these sectors. So if you're going to build a model of the climate change impacts on these various sectors, and the model is a mathematical model, and you have to write down equations for that impact, it really forces you to be rigorous and to think about it deeply. You can't just hand wave away like, oh, it causes something bad in this sector. And it makes you come up with numbers and not just adjectives for the impact. And then you can compare what is the impact between various sectors. So I'll just kind of like go through these quickly here, just to show you the type of thing that's going on in these models. So like agriculture, for instance, there's some countervailing effects that they're modeling. So they say the impacts of climate change on agriculture at time T and in region R, so they have this broken out into different regions, are split into 3 parts. So they have the 3 parts are impacts due to the rate of climate change. So they have something due to just the rate, how fast the climate is moving. They have impacts due to the level of climate change, so what the climate is, what the temperature is, and impacts from carbon dioxide fertilization. So that's interesting. They're adding this effect that we're increasing CO2, and that has an effect on agriculture. That has an effect on plants. It's not just through temperature that you're going to get impacts on agriculture. And so they say the first part, the rate, that rate of climate change, is always negative. So it always hurts agriculture for the climate to be changing. So there you're kind of assuming that you're starting from a point where the agriculture is adapted to the current climate. So change is always going to be bad. So that's always negative. So faster climate change is greater damages. The third part, CO2 fertilization, is always positive. So it always helps this always helps agricultural productivity here. And the middle part, the second part, can be positive or negative. So it's saying there's an optimal climate for agriculture, and some locations on Earth are too cold, they're below that optimum climate for agriculture, and some locations are too hot, they're above that optimum for agriculture. So depending on where you are, that can be a positive or negative impact on agriculture. So then they talk about how mathematically they represent these 3 terms. But the point is just it makes you think about the various impacts, and it makes you write down an equation that you think is the relationship between climate and that thing that you're looking at. And these equations, again, they're not physical laws. They're not like the relationship between CO2 and global temperature. They're kind of made up. Like someone thinks that I think this relationship exists, and then I can look in the data to see if it is borne out. But it's not the same thing as these physical laws. And then they end up converting it to, like I said, in order to get the damage function, you need to convert it at some point to productivity or to GDP per capita. So then they discuss how they do that. Going back to this middle part and this CO2 part, so the optimum climate part and the CO2 part, when we look at kind of more sophisticated modeling at the level of the crop, we get some interesting results with that. So that's what this study does in Nature Food. It came out recently. Climate impacts on global agriculture emerge earlier in new generation of climate and crop models. And I want to show you something pretty interesting from this. This is so we have 4 major agricultural staples up here: maize, so corn, wheat, soybeans, and rice. So these constitute a huge portion of global calories consumed. Then we have global productivity change. This is due to climate change. And green is under a lower emission scenario, and yellow is under a higher emission scenario. So first look at corn or maize. We see that these climate crop models project something like a 7% decrease in maize production due to climate change under this lower emission scenario, and then up to like a 25% reduction under this higher emission scenario. So warmer temperatures really harming corn production. But if you look over here at wheat, that's above the zero line. So these climate crop models project an increase in productivity from wheat of like 10% under this lower emission scenario, and a higher increase under this higher emission scenario. So getting up close to 20% increase. And then soybeans and rice are less sensitive. But we can look at like where that is, what that looks like in time and in space. So here's our negative impact to corn over here, and these reds and yellows are decreases in yields, where greens are increases in yields. And so we see over most of the globe a decrease in corn yields, and then that decrease gets larger over time. But then wheat, most of the globe sees an increase in wheat yields. And so it can depend on the crop. And the main difference between these two crops here, if you are familiar with this, taking some biology classes, has to do with their photosynthesis and whether they're C3 or C4 plants. And so maize, the corn, as a C4 crop, is basically not helped as much by CO2 fertilization as wheat is as a C3 crop. So wheat in these models benefits a lot from being more CO2 in the air. And then the other factor that they talk about is that wheat tends to be at these higher latitudes where it's temperature limited. The reason that there's not more production is because it's too cold, and so warming increases production, and there's less wheat in the tropics, and so that's not going to be harmed as much. Where the maize, there is more maize or corn in the tropics, and so that's harmed more. The point there is just that it's complicated, and it might depend on the crop itself when you're talking about agricultural productivity. Looking at some of these other ones, energy consumption is an interesting one. This is another one that's probably going to be a little complicated, right? That it's not obvious what the sign is ahead of time. So they have two equations right away for energy consumption in this model. They have energy for space heating, right? We want to heat our spaces when it's too cold, and energy for space cooling. We want to cool our spaces when it's too warm. And so as it gets warmer, what do we expect? Like, which one of these is going to change more? So this is another one that's ends up being pretty complicated, and there's the literature, the papers, the reports are all over the place on which is bigger. This is a high-profile paper that came out in Nature last year called "Estimating a Social Cost of Carbon for Global Energy Consumption." And in this one, they say that previous estimates have suggested that large warming-driven increases in energy expenditures could dominate. This is basically saying that previous studies have shown that climate change should increase energy expenditures because of more cooling requirements. But here we show that the release of 1 ton of CO2 today is projected to reduce future energy expenditures. And so they're basically trying to weigh these two equations. This, as it gets warmer, you have reduced need for space heating and you have increased need for space cooling. And what does that look like over time? And then you have to make a bunch of projections of how various regions will develop, and population changes and infrastructure changes and all of that. And one of the interesting parts here that emerges from that is that they say that we project that emerging economies in the tropics will dramatically increase electricity consumption owing to warming, but because global data indicate that many populations will remain too poor for most of the 21st century to substantially increase energy consumption in response to warming. So they're saying that at higher latitudes you have decreased energy use with warming because you don't have to heat your spaces as much, and at lower latitudes you have increased energy use with warming because you need more cooling. But if populations aren't rich enough to have air conditioning, for example, then you don't get that increase in energy consumption. And so there's this additional modeling that needs to be done about GDP per capita and adoption of the energy infrastructure itself that goes into this. So here's their map of changes in energy consumption, both with electricity and with other fuels. So the blues are decreases and the reds are increases. And so as it gets warmer, most of the tropics has this increase in energy consumption, especially from electricity, because air conditioning is dominated by electricity, where other fuels tend to decrease over over all of the world, because other fuels like natural gas tend to be the fuels that we use for heating. So it's a complex function of space and depends on a bunch of other factors. And so it's not clear exactly how climate change will affect energy consumption. Another thing that gets talked about a lot is climate change's impact on energy production. So like our power plants require water, because we boil water to spin turbines in all of our power plants. And then there's obviously hydroelectric power, which depends on water. And then wind and solar are going to depend on the climate itself. So that's another thing is climate change's impact on energy supply, where this is energy demand or consumption. But there's not a clear indication of even what the sign of the change necessarily would be for changes in energy consumption. Sea level rise is going to be negative no matter what. I don't know of a plausible pathway by which sea level rise stimulates economic productivity. Ecosystems, that's one that it's really tough to model in an economics model. Some just leave it out and say, listen, ecosystems are not part of the system that we're trying to model. So that's a separate issue that we can just look at separately. Some try to include it, but then you have to monetize it. You have to come up with some dollar value. And so one way of doing that, which I think is a pretty weak way, is to try to come up with some measure of how much people value ecosystems, either by looking at tourist statistics or something like that. In this case, they say the warm glow effect, the value which people are assumed to place on such impacts. So in this model, they try to include that and try to monetize that. They look at these dimensions of human health, which might be temperature dependent. But you can always ask the question of okay, why just these two? Why are these two broken out, diarrhea and vector-borne diseases? Vector-borne diseases tend to get a lot of attention just because it's pretty clear that there's a relationship between temperature and mosquito habitats or mosquito areas. So that kind of makes sense. Diarrhea is a huge global health problem. And since primarily works through dehydration, I think that's the main reason why we think it's temperature dependent. It may have to do with the main viruses as well. But yeah, so the point is to come up with an equation that has temperature on this side and the thing that they're trying to model on this side. And these equations are very much up for debate, both what the values of the parameters are and what the equation itself should look like. Yeah, let's look at this. So mortality from basically hot and cold weather. So we see statistically in the data that you get excess deaths in hospital data when temperatures are far away from human comfort levels. So people that are very sensitive, elderly, infants have worse health outcomes, and you actually see more people die when temperatures are away from kind of our comfort level of 60, 65 degrees Fahrenheit. So then you can try to assess what changes in temperature might do to these outcomes, to mortality, morbidity outcomes. So first, do you think more people die from it being too hot or too cold? Then where do you think most of the cold deaths would be, the too cold deaths? So I'll show you this map here from this paper. Okay, so this kind of answers those questions of, we have cold-related deaths estimated globally. These are excess deaths beyond some baseline rate, and then heat-related deaths average globally. And you see that this color bar here for the cold-related deaths is much larger than the heat-related deaths. So actually, we do see a lot more people die from it being too cold than it being too hot. So that's one thing. Another thing is that I would have said that I would expect most of the cold deaths to be where it's cold, right? But this is actually not the case. So looking at where most of the cold deaths are, let's look at Europe, for example. Europe experiences even though Europe is relatively cold, Europe experiences much less cold deaths compared to heat deaths. And Africa experiences much more cold deaths than heat deaths. I mean, this is really showing adaptation, that Europe is adapted to the cold. And so there's more, you're more likely, if you think about Italy or these places along the Mediterranean, it's very much like San Francisco, where we have this Mediterranean climate and we're set up for, most people have heat, but they don't have air conditioning necessarily. And so when you have a strong heat wave in that area, even though it's not as hot necessarily as it might be near the equator, the population is more sensitive to that, and so you actually end up with more deaths from heat in these colder locations, and then more deaths from cold in these hotter locations. I mean, I am surprised myself there's not more heat-related deaths in Africa. There could be data problems here. One thing I was thinking about is that, we fundamentally are a tropical species. We evolved in East Africa right here, and so fundamentally we're kind of evolved to be at a temperature like that, and it was only through technology and clothes and all that stuff that we're able to populate these other parts of the world. This is interesting. It's another thing that makes all of this stuff very hard to quantify and to put into a model. Let's see. So here's looking at projections of changes in heat-related excess mortality, people dying from temperature change, and they basically say that more people die from cold today than heat. But as it gets warmer, it's about the changes in those two things, and so it can be the case in some of this modeling that the increase in heat deaths outweighs the decrease in cold deaths. But it depends on the location, depends on the region, depends on the emission scenario, depends on various assumptions about adaptation, all of that stuff. So it's tough. It's tough to quantify these types of things. So then they also talk about here tropical storms and extratropical storms. And so I thought I would just take a second to show you the types of weather disasters within these extremes that tend to be the most expensive. This is from the NOAA $1 billion disaster database. So they, from 1980 to the present, have recorded all of the $1 billion weather and climate disasters. And then this is the ranked by most expensive to least expensive. And so the vast majority of the very top ones are tropical cyclones. And then we also have some flooding events, wildfire, winter storms. So that's going to be an extratropical cyclone, flooding, severe storm. That's extratropical cyclone. Here's what those $1 billion disaster counts look like in terms of month of the year. So you can kind of see like when these tend to happen. We can see this like relatively distributed. Most expensive ones are these tropical cyclones, but it ends up being the case that they don't have necessarily the huge frequency difference compared to some of these other things. So severe storms like tornadoes and hail and happens in the spring in the Midwest of the United States. Those dominate these months. And then over here in the fall, then that's when we get the wildfires come up and the tropical cyclones. So what would be like some of the problems then with these bottom-up assessments? Like one thing I can think of is that when we look at this list here, so in addition to the issues of like all these things just being very difficult to quantify and you're not even sure like what the sign is on some of these changes, one thing would just be like you're leaving stuff out, right? So there's actually nothing in here. So they have extreme weather tropical storms, extreme weather extratropical storms. But if we look at actual data here, wildfires are in here, and there's no wildfires in that model. So you can just totally neglect something, just forget about it, that's super important. We've seen this in California that wildfires may be our largest climate impact. And again, it's just completely left out of that model. And it might, impact the economy in a bunch of different ways, that you'd have to spend more money on programs to try to prevent ignitions. And, you're definitely spending more money on things like suppression costs, fighting fires. So this is a measure in millions of dollars, and showing that going up dramatically as fires have gone up dramatically. Then you have utilities putting a bunch of money into, for example, burying power lines or other programs to reduce wildfire frequency. You have health impacts from smoke increases. This is a study of the economic footprint of the wildfires that occurred in 2018 in California. Again, these are not climate change assessments. These are just what's the economic impact of the wildfires. So only some portion of the increase in wildfire activity has been due to climate change. But this is very interesting, showing that our estimation shows that wildfire damages totaled 150 billion, which is 1.5% of California's gross domestic product. So that's big, because it's just wildfires itself, which are just concentrated in one small portion of the year. And the way they break this out, they show that only a small percent of that, so only 20% of that was actually like losses from buildings, and 22% was health costs, basically from poor air quality, and then 60% was indirect losses. So affect industry sectors and locations distant from the fires. So like supply chain disruptions and just kind of all of the other disruptions to economic activity that came about from, this is mostly from that campfire in Paradise. So that's another issue with these bottom-up assessments, is that you can just miss things. You can forget about things because you basically brainstormed what sectors are most important, and you can miss some. So that leads to this other idea of doing it top down instead of bottom up. And so instead of first trying to estimate all of these individuals and then add them up to get an estimate of the damage function, you could say, let's, instead of doing that, just look at what is the relationship between temperature and total economic productivity at like the level of a country, for example. So then we don't really know which sectors are impacted. We don't know why temperature might be affecting the whole economy, but at least we know we can estimate like what the net total effect of that is. And this is a paper that does that top-down estimate of the damage function, a paper called Global Nonlinear Effect of Temperature on Economic Production. And so again, the idea is they're trying to figure out what is this damage function? Damage function being, and the relationship between temperature and GDP. And so you could think about like there's different ways that you could do that. So one way you might think about doing it would be looking at this relationship across space, because we have obviously countries with very different levels of GDP per capita around the world, and we have temperatures for those countries that are very different. And it turns out there actually is a relationship between these two things, that warmer countries tend to have lower GDP per capita. But it's very difficult to say that that's a causal relationship. Some people do speculate that there's some cause and effect there, but like so many historical contingencies, so many things going on that are causing GDP per capita to vary between countries, that it's difficult to say like it's temperature that causes that difference across countries. So probably not going to use a relationship like that. You could also look at historical climate change and changes in GDP per capita over time. So like if you looked at, for example, this is temperature in New York City. So temperature from the 1850s to the 2000s increased by 3.5 degrees Fahrenheit. And of course, GDP per capita increased in New York over that time. But you can't assign causality to that, right? Like we know, the reasons for increasing GDP per capita that we talked about last time, specialization and technology change, those types of things. And so you're not going to say like, oh, it's temperature, that increases in temperature caused the increase in GDP. So how might you do this? Well, what this paper does is something that's pretty clever. They say, look, okay, the temperature associated with climate change has been an increase of about 3.5 degrees Fahrenheit from 1850 to the 2000s. But if you actually look at like year-to-year variability, there's kind of just as much temperature variation over these yearly timescales as you see over the long run. And so if you were able to use these year-to-year fluctuations to find a relationship between temperature and GDP per capita, you could be pretty sure that it is actually temperature that's causing that change, because there wouldn't be like some confounding factor. It's not like some technology change shifted a lot during this short time period or something like that. But so if there is a relationship at this time scale, you would think that it is actually caused by the temperature change. And so that's what they do. They look at country by country, the relationship between hot or cold years and GDP growth in that country. And what they find is that the relationship is not really good. It's not very clean anywhere, but you can kind of see it in various locations, that some countries, when it's warmer than average, they tend to have higher than average GDP growth. In some countries, when it's warmer than average, they tend to have lower than average GDP growth. And you might say, well, what's the difference? Why do some countries have this negative relationship and some countries have this positive relationship? And it turns out it's where the country is in terms of its baseline temperature. So cold countries, when it's warmer, their economies grow a little bit more. So Iceland is over here. And then warm countries, when it's warmer, their economies grow a little bit less. The United States is kind of right in the middle. So the United States is like right on this optimum level. And so what this is showing is there's basically an optimum temperature for economic growth, and it's around 13 degrees Celsius, right where the United States is, and that's like 55 degrees Fahrenheit. We are right at the temperature for optimum economic growth. And so you can then use a relationship like this to come up with a top-down estimate of this damage function. So it's like you take this relationship between economic growth and temperature. We move the countries in terms of, they would all go to the right in terms of their temperature, and then you calculate what that would do to global economic production over time. And so that's what they do in this paper. And here's a map of what they come up with, percent change in GDP per capita at the country level, showing that warmer countries that are on the warm side of that optimum, are harmed by further warming, and countries that are on the cold side of that optimum are helped by warming. And so Europe, according to these calculations, has this increase in GDP per capita due to climate change. North America is kind of steady, and then a lot of these other regions then are large decreases because they're already on that hot side of the optimum. But then this is their global estimate, is a 23% reduction in GDP by the end of the century. This is this Burke estimate that I showed you in En-ROADS. So this purple one, Burke, here is in En-ROADS. So that's where that comes from. And here's my last point here, some of the downfalls of these top-down estimates. So at least you're kind of including everything, but what it doesn't include are basically that you're looking at weather variability, and you're then assuming that that's going to be the same thing as the climate change impact. And so it wouldn't include any type of adaptation, where you can imagine, like, if it's really hot, say 1 year, and you lose all your crops, does that accurately represent what would happen if it's that temperature every year? And probably not, right? Because if it's that temperature every year, you can't just count that, like, that crop loss is going to happen every single year. The farmer wouldn't plant those crops. They would go somewhere else. They would plant a different crop, something like that. So this estimate does not include that type of adaptation that would mitigate those temperature changes. But on the other side of things, it also doesn't include possible intensifications from it being a climate rather than a weather event. So this example here, they say, consider agriculture. A drought in a single year may have little effect if there are ample stores of water available in a reservoir. And then, on the other hand, if the amount of rainfall permanently decreases and the reservoir eventually runs out, then the supply of water to agriculture will fall substantially, with impacts on economic activity. So the fact that that temperature change would persist and be there every single year would actually make it worse than the weather variability in that case. And then in this adaptation case, the weather variability would be worse than the climate change issue. So those are some of the downfalls of the top-down assessments. And so that's kind of, why we have these wildly different estimates, where, it can be from a few percent up to a huge portion of GDP per capita estimated to be damaged from climate change. And so that's just where we are in terms of trying to quantify this issue. So it's super important, but it's just not very well defined the same way that some of the physical science of climate change is.